So whenever we are dealing with categorical data, or then only we talk about proportions, because it cannot be modeled as numbers because they are not numbers. Okay. So that is, so when we are dealing with categorical data, yes, no, success, failure. Okay, that kind of success, failure, we have seen that. Okay, so I'll do first one sample z test of proportion. So this is there. So as I've said earlier, this is comparing. What does it compare? It compares the sample proportion. I have mentioned this earlier. Let me just check. Okay, I just mentioned it. Okay, I didn't write it. Okay, so let me write it again. I thought I have written it. So what it means is that it is the observed proportion comparing, when we are comparing two. So this is to one sample, right? So we are comparing observed proportion, compare observed proportion to a known hypothesized value. So one side is fixed, so other side is only come from a compare observed sample proportion to a known hypothesized value. So we have the sample from the sample, one sample we have, and the other side is fixed, that we know that this should be the value. And when we compare these two, this is one sample, and in the two sample, both are independent groups. Okay, both are independent samples. So this is there. Let's put the so next thing is the we have the test statistic. So what will be the test statistic for this? For n test, we have the test statistic, like we had for t test, z test. All the tests will have a test statistic. So it is called z. Okay, as because it's a z test. So it will be similar. So let me define all the terms. So what was the p hat? P hat we have defined. This is the proportion of success. That is equal to x by n. Okay. Then there is something called p naught. That is a specific proportion. Okay. Under null, this is specific proportion or the hypothesized value. Specific proportion under null hypothesis. Okay. Consider null hypothesis is true. So that is a specific proportion or the hypothesized value. This is this against which we are going to compare. So p hat and p is defined, and now standard error we know. So this will be standard error. 0 is again the standard error under null hypothesis. H0 is null hypothesis. Okay, and the z statistic. So what will be? So my z is defined as, so this is your z observed or t observed. This is your t observed generally is equal to z observed. You can write this. And this is your difference of the proportions. So this will be p. Let it be 2 only. This is your specific, or this is a hypothesized value. Okay, and this will be divided by the standard error. So what is the standard error? So generally that is used for standardizing. So here it was p into p naught into 1 minus p naught by n, right? So this term is a standard error. Other terms we have defined. N is the number of samples. Okay, standard error we have defined already. So this is your variance, square root of variance, and this is coming from the central limit theorem. Simple. This is your test statistic for one-sided z test of one sample z test of proportion. Okay. So this is simple. These are the two proportions. That's how we do. In case of means, we compare the two means, and there is a standard error below, or some form of standard deviation. So standard error is a standard deviation only. Okay, but of the observed statistic, and we infer something from that. So this is a kind of standard deviation only. Standard error. It's nothing different. So let's do next two sample test. Two sample z test of proportions so this is again test if there is a significant difference between the proportions of two independent samples. Okay, this is to compare two independent sample proportions. So both the values are coming from two different samples. Earlier one side was sample from the sample, other was hypothesized. Okay, so that's the difference. That will be the running difference everywhere. And then generally this is the most, okay, this is why it is important. So just make a note. This is the standard test used in A/B testing. Okay, this is the standard test used in A/B testing whenever we have categorical data, right? This is the standard test used in A/B testing. Okay, we will do an example so that will make it amply clear. And what is the, how do we define it? There are more terms here. So there is one P bar, okay, which is your average of total success, that is total success. This is average across both the samples, okay, by total success in both the samples by total sample size. Total sample size, that is across both the samples. What is my total success? So that is total success will be x1 plus x2 if there are two samples by n1 plus n2, right? So it can also be written as, because my p hat is equal to x by n, this implies x can be written as n into p hat. Okay, so if I replace this x by n p hat, so this will be n1 p1 hat plus n2 p2 hat by n1 plus n2. So in case we have to define it in terms of this one, p1, we have this, if these proportions are known. Okay, same thing. And now what is my standard error? This p hat is for combining the two success proportions. Okay. Then we have the standard error. Standard error term in the denominator. So this is standard error for P1 and P2. For both the samples, this will be equal to square root of, and that's why this average P bar is used. Okay, so that is equal to P bar into 1 minus P bar, and then into 1 by n1 plus 1 by n2. N2. So these are the sample sizes of two samples, and P1, P2 are the proportions of the two, and I take an average of, this is the way we take the standard error. So how do we take a average of this? This is the way we take the proportions of both the samples into account and make it into one standard error. Okay, and now simple, we have both the terms sorted. So my z statistic will be z statistic or test statistic when I talk in terms of hypothesis testing, or this can be equal to t observed, or this is equal to z observed, whatever, when whatever you are observing under null hypothesis. So this will be equal to p1 hat minus p2 hat. So the difference between two proportions minus divided by the standard error. Standard error is given by p hat into 1 minus p hat by into 1 by n1 plus 1 by n2. We know all these terms. This is the proportion of success of first sample, proportion of success of second sample. Let me write it. Proportion of sample, another terms are known. This is sample size. Okay. So these are just formula, just put the numbers, okay, and then you will get the values out. So just plug in the numbers. If you understand the concept, now plugging in the values will be very easy. So if this is clear, let's do a quick problem and understand this. Okay, I hope this is clear. The two sample test. It is just formula. This formula is coming from a derivation. So it's in a general format. Always we have some kind of difference in the top. in the numerator, and the denominator has some form of standard deviation. Let's move. So let's do a question. So we are doing A/B testing to compare the two designs of a website. Okay, so we are doing A/B testing to compare two designs of a website, and we have some data. So after, from this design, how many users signed up, etc. So if I have that data, so I can, from that I can do test of proportion and find out which is a better design. Okay, so I have A/B testing to compare the two designs of website and to see if, and my claim is that the design, there are two designs, A and B. Okay, so there are two designs, A design and B design, so for the name, and my claim is that B increases the conversion rate. This is my claim. So maybe A is the existing design and B is the advanced design. Maybe the color of some button is changed or the web page font is changed, something, some minor change has been done, or major also. And then I say that the new change, which is measured by B, increases the conversion rate, and for that I'll have data, and from that data we'll do the z-test of proportion to understand whether the claim is true or not. And this is a hypothesis testing. We make a claim, and then with the data in the sample we validate whether the claim is true or not. Okay, so let's move. We increase the conversion rate. Conversion rate, that is proportions of visitors who sign up. Conversion rate means proportions, again it's fraction, right? Proportions of visitors who finally sign up after visiting your page. Okay, so that's the test. So let me write. So you have group, okay, and then we have number of visitors. Okay, so this is your n, and then there are number of signups. So this is a success, this is x, so this is total number, and out of that how many signed up, that is your success, total success coming from binomial. And then this is your conversion rate or the proportion conversion rate. This is your p bar is equal to x by n. So let's write, there is group A, group B. Say for example here 1000 visitors here, and in the group B you have 1200 visitors. Here 80 people signed up, here 114. I'll do the maths, okay, and I'll leave up to you to verify that quickly. And what will be my conversion rate here? So if this is a, PA will be 80 by 1000. So this is clearly 0.08. This is simple. And then PA for B would be, the proportion for B would be 114 by 1200, and I have computed this already. This comes out to be 0.095. Okay, and the numbers you can just put it and validate. I'll just keep on writing. The main idea is to understand how do we do hypothesis testing for the categorical data which is coming from z-test of proportions. We have understood the theory, and let's put the numbers. So how do we do hypothesis testing? Let's follow the thing. The very first thing that we do is, let's solve it, that we fix our null and alternate hypothesis. So what is our null hypothesis? That proportions of both are same. There is no difference in conversion rate. So I say that the proportion of conversion is no difference in, there is no change. That's what is null hypothesis. No change. That implies proportion A is equal to proportion B. There is no change. No change in conversion rate. That's what null hypothesis means. There is nothing has changed. There is no difference. Status quo is maintained. And what is alternate hypothesis? So that's the claim that I am making. Depending upon that, the kind of test, whether I am doing a right tail test or left tail test, one-sided test or two-sided test, that will be determined. So here I say that B increases the conversion rate. So my B design is better. Okay, that's what I want to say. Okay, there are two designs, and design B increases the conversion rate. So I say that proportion B is greater than proportion A. Okay, that is B is better design in terms of conversion rate. Okay, B is better design. So whenever we are comparing greater, something is greater than, so this will be a right tail test, and again this will be only one tail test, because if it is not equal to, then we are comparing on both the sides, less than or greater than. But we have only one side, less than or greater than. If it is greater than, I move to the right tail test. If it is less than, I move to the left tail test. Okay, as simple as that. So let's move. This will be a one-tailed. Okay, that will be a right-tailed test. And let's put the formula. And also let's check the large number condition, sample condition, whether I have enough samples or not. So the large sample condition, so that it can be approximated. The binomial can be approximated as normal, because from there only all the formula has come. So large sample condition, what is the large sample condition? That number of successes should be greater than or equal to 10. What is our number of success here? NP, that is your X, total number of success. Here it is, it should be, no, not 1000. It should be greater than or equal to 10. Here clearly this is 80. Okay, and the number of failures should also be greater than 10. So clearly if success is 80 and we have 1000, so this is greater than 10. So no problem with this. So always make, I'm just pointing it out because do this test if you have small sample size. Okay, you count the number of success. We have 80 here, so it is clearly greater than 10, and the failure is the remaining 920, so it is clearly greater than 10. I hope that makes sense. And then we consider with the, continue with our test statistics. So we have this null hypothesis and alternate hypothesis is fixed, and then what kind of test we are going to do? So we are going to do a, we have finalized here itself after doing this, that this is a one-tailed right tail test for, and this is a Z test. Okay, this is a two sample test of proportions, because I am comparing proportions. So this is my test, and then for that, what will be my test statistic? So my test statistic is, so checking by the distribution, the underlying distribution is normal, but the test statistic which we will measure is what is the formula here? This is the formula. Let me copy this. I'll put the values. And where P bar was equal to, what was P bar equal to? This square root of, I'll just copy this. No, not this one. What is the, this is the P bar, right? This is the P bar. Okay, sorry, this is the P bar. Because I have written it already. So P bar is equal to this. Because I need to use P bar in the formula. So all these values are already present. I have x1, x2, that is xa, xb. This x, this is there. And n1 and n2 are there. This is n1 and n2, na, nb. So I can directly compute P bar. So my P bar will be equal to na is 80, nb is 95. No, 114. Sorry, 114, and the denominators are 1000 in one sample and 1200 in one sample. I have calculated this already. This should come out to be 0.088. Okay, this is a P bar, and then rest of the numbers. So let's calculate the standard error. Let's calculate the denominator separately. This is my standard error. Okay, so this is my standard error is equal to this. Okay, the square root is on complete thing. So this is equal to P bar is 0.088 into 1 minus 0.088. This will be, whole thing will be under square root, and this will be 1 by n1 is 1000 plus 1 by 1200. If you compute this, this should come out to be approximately equal to 0.0123. This is just calculator. Okay, and then finally my Z observed or equal to T observed. If I talk about test statistic, generally it is Z observed. Okay, whatever the test statistic I'm measuring, so this should be equal to because I'm measuring whether PB is greater than PA or not by standard error. So my PB is what is my PB? We calculated earlier. 0.095 and 0.08. So 0.095 minus 0.08, and the standard is 0.0123. Okay, and this will approximately come out to be 1.22. So this is your final Z observed. What to do next? So this we have to compare against the z-score. So this we have got the test statistic value we have got. Now we have to find the alpha. So what is your alpha? Alpha is say 5%. Okay, so this is your 5%. This means that this is your 0.00. This is your significance level beyond which, okay, if your null hypothesis will be accepted or rejected. This is determined by your alpha. So, and this is a right tail test. So we have found out that is a normal distribution. Here your mu is there, and now we have found out that your z observed is equal to 1.22, and for, so this is my p value. There will be some area under this corresponding to this. Okay, so this will be my p value, that is equal to area under curve for this probability of observing t greater than equal to t observed or d observed. T value is probability of observing t value greater than equal to t observed. This is the t observed, z observed. Okay, this is the area under the curve. Now, if for this significance value level, okay, this significance value level or whatever significance value, I think, for this significance value, if it is coming here, okay, my t alpha is coming here, so this is so my z observed is greater than this, so this is greater than 5%, so I will accept my null hypothesis. But if my t alpha or the critical value comes here, means the area under p value is less than 5%, so I will reject my null hypothesis. So how do we find out? So what will be the z score for alpha is equal to 0.5. So my z score, because this is normal distributed, for alpha is equal to 0.05, 5% significance value. So this will be equal to how much? So let's see online. Where is it? So this is a chart. You can just search for z-score table PDF, and then you can scroll through this. And here if you see hypothesis testing critical values is here, and here if you see 0.05 is the significance level. And for left-tailed or right-tailed test, left-tailed is minus 1.645, and for the right-tailed we have right-tailed test here because it is greater. It is 1.645. So this is equal to 1.645. So this is definitely, okay, this is definitely greater than 1.22. Okay, just a minute. So I will just make it here, and this is your t alpha. This is equal to 1.645. This is more right. This means that the area, so this value will be, okay, let me color it for you. So this value is your significance level or significance value. Okay, this is 5%. So definitely my area under the curve, the p value, this shows that my p value is greater than significance level, which is 0.05 or 5%. The area under the curve on this side will definitely be, because there is some more area under the curve under this. So this is greater than this. Means we fail to reject the null hypothesis. So what is the conclusion here? We fail to reject null hypothesis. So what is the conclusion? That whatever changes we are observing, that in the conversion rate, that we have observed, that is due to some random chance. It's not because the design B is better, because we have calculated here that for this significance level, the area under the curve is less than the significance level, so we fail to reject the null hypothesis. This means that, what was the null hypothesis? There is no change in conversion rate, and whatever we are observing, okay, that is not statistically important, it's significant, and that is just random or by chance. So whatever improvement in the conversion rate we have seen, that is because of some random chance. I hope now this is clear. We have rejected the Now, we fail to reject means we accept. Okay, we accept null hypothesis. We fail to reject, or other words we can say, but generally we say we fail to reject. I hope this is clear. So the conversion rate, whatever you have seen, we have seen clear improvement here, right? This is from 0.0 to 0.9, but after the test of proportions, we found out that this is below the significance level. So this is by random, by chance, and is not because design B is better. I hope Z test of proportions is clear.